Hello everyone. Welcome to this lecture starting multivariate random variables. This is going to be based on chapter 3 of the Demidonco's textbook. In this lecture, I'm going to talk about several topics, including joint and marginal CDF, joint and marginal VMF, joint and marginal PDF, and then expected value and the independence. These topics will be included in 3 videos. Each video will be roughly between 45 minutes to 1 hour. So we will start with a discussion about why we need to learn about multivariate random variables. Up to now, we were talking about univariate random variables and their properties, expected values, distributions, and so on. But in many real-world situations, we have to deal with several random variables simultaneously. We have to study their relationships, behaviors, and so on simultaneously. So in that kind of situations, studying the variables one by one is not uh, sufficient. Right? Marginal distributions alone are not sufficient to describe the complete behavior of multiple random variables. Especially in that case, we will not be able to capture the dependence or dependencies between variables. But when we study the multivariate random variables, they allow us to formally define and study concepts such as dependence and independence through the joint distributions and conditional distributions. So therefore, multivariate random variables and studies using multivariate random variables is very useful. There are separate multivariate techniques where we use multivariate random variables. In practice, there are many practical problems in statistics, engineering, economics, and natural sciences, and other fields where such multivariate random variables are important. So therefore, this part of study on multivariate random variables will be very useful to you in your future statistics applications. So we will now move on to the theoretical part, starting with some definitions. And these definitions are actually direct extension of the univariate counterparts. We have already looked at the univariate uh, definitions of univariate CDF, PMF, and PDF. And you can see that these are direct extensions. Anyway, we will, just for the completion, we will go through them. The first definition is about joint cumulative distribution function. Let x and y be two random variables. The joint or bivariate cumulative distribution function is defined as the joint probability, that the probability capital X less than or equal to some simple X real number, and the capital Y less than or equal to some real number, simple y. So that is how the cumulative distribution function, joint cumulative distribution function of the two random variables X and Y evaluated at the real numbers, simple x and simple y is defined. We are starting with these bivariate definitions because it is easy to understand and sometimes we can graphically show them. That's why we are dealing with two random variables at the start. Later on, we will move on to more than two random variables. But most of the definitions will be uh, done in terms of using two random variables. So this definition is valid for discrete random variables as well as for continuous random variables. But for the discrete random variables, this having this less than or equal sign, capital X less than or equal to simple x, and capital Y less than or equal to simple y is important. For continuous random variables, whether you have equal sign here and equal sign here or not, doesn't matter that much because the value, the probability will be the same anyways. So this is the definition of the joint cumulative distribution function. We are looking at now by this comma, actually we mean the intersection here. This x less than or equal to simple x is an event. Capital Y less than or equal to simple y is an event. So what we are really looking at is the probability of the intersection of these two events. But when we write down the events in terms of random variables, uh, usually we don't use those set notations. Instead, in order to show the intersection, we use the comma. So, but you have to understand that here we are looking at the probability of the intersection of two events. So it's a probability. So what are the properties of the bivariate cumulative distribution function? Because it's a probability, it has to be between 0 and 1, right, inclusive. And then when keeping the value of one variable fixed, when we let the other value of the variable goes to infinity, negative infinity, then the value of the cumulative distribution function is 0. And also, if we keep one value of the variable fixed and let the other value of the other variable to infinity, then the cumulative distribution function becomes 1. Right? If we set both values to infinity, still it is 1. Right? So this is again a generalization of the univariate case. We know that the cumulative distribution function starts at 0 from negative infinity and reaches 1 at the positive infinity. This is the same idea, right? But even though one value of a variable is not infinity, if one value, the other value is infinity, then according to that, the cumulative distribution function will be 0 or 1. If one value is at negative infinity, then it will be 0. If the value is at positive infinity, then that value will be, cumulative distribution function will be 1, right? And similarly, if you consider two values x1 and x2, so that x1 is less than, keeping y fixed, if you consider the cumulative distribution function at x1 and x2, keeping y fixed, then the cumulative distribution function, joint cumulative distribution function at x1 will be less than or equal to the joint cumulative distribution function at x2, because the cumulative distribution function, joint cumulative distribution function, is a non-decreasing function. It's a non-decreasing function. In this case, when you are dealing with two random variables, it's going to be a non-decreasing surface, right? So even if you keep y here, this non-decreasing property is there. If you keep x fixed and consider two values at y1 and y2, then again, because of the non-decreasing property, the cumulative distribution function at a lower value y1 will be less than or equal to the cumulative distribution function at upper value. So these both properties are actually because of the non-decreasing function property. And here I have given you the expression that you can use to find out the probability that your capital X and capital Y will be in a certain rectangle, right? Here we are looking at the probability that capital XY point, random point, falls in this particular rectangle, X1, X2 interval into Y1, Y2 interval. So that gives you a rectangle. But notice here, X1 is open, that means X1 is not included in the interval, but X2 is closed, that means X2 is included in the interval. And similarly, this interval, right? So this is very important when you are dealing with discrete random variables. But for continuous random variables, it doesn't matter whether you include or exclude that point. The answer will be the same, right? So what it says is that probability that capital X is in this particular interval, including X2 less than or equal to X2 but greater than X1, Y less than or equal to Y2 but greater than Y1 will be given by this expression, the cumulative distribution function at joint cumulative distribution function at x2, y2 minus the joint distribution at x1, y2 minus the joint cumulative distribution function at x2, y1 plus the joint cumulative distribution function at x1, y1. This is very easy to understand if you look at this picture. What we want is actually the probability that xy point, what we want is the probability x comma y point in this particular area, say A, for example, this area here, that is SA. So, this, of course, the cumulative distribution function will be over this support. If we want to find out the probability that xy point in this particular A, you can find out uh, the probability that xy point is in this whole area. That means less than or equal to this is x2, this is y2. The probability that x is less than or equal to x2 and y is less than or equal to y2. So that is this whole area that is given by cumulative distribution function of x, y, x2, y2. Subtract, then subtract from that this area, right? Subtract this area, so that will give me going off, and then also subtract this area. So that means, so then you can see that this area will be subtracted twice, right? So you have to add that once. So therefore, that's why you have this particular expression. The probability that xy is in A is equal to the probability that xy is in this large rectangle minus the probability that it is in this rectangle minus the probability that it is in this rectangle plus the probability that it is in this rectangle. So that all those things can be written in terms of cumulative probabilities. So that's what I have been done there. Right. Okay. So now, having defined the joint cumulative distribution function, next we define marginal cumulative distribution functions. These are the same as what we learned earlier, individual cumulative distribution functions of x and y. But if you were to get the marginals cumulative distribution functions of x and y separately from the joint cumulative distribution function, what you have to do is let uh, one value to infinity, then you get the cumulative distribution function of the other random variable. For example, if you want to get fxx, then you have to set y to infinity here, right? So that you get this cumulative distribution function of x at evaluated at simple x by letting y in fxy simple x simple y, letting simple y to infinity, right? So that's the limit y goes to infinity fxy xy. So this x here is the same as this x, but y have to be infinity. And similarly, if you want to get the cumulative distribution function of y, you have to set x equal to infinity in the joint cumulative distribution function. So that's uh, very clear, right? So with here, this means the probability x less than or equal to simple x is the same as probability that x less than or equal to simple x and y less than or equal to a positive infinity. So y can be anything, what we are interested in, the event that x less than or equal to simple x. In this case, we want the probability that capital Y is less than or equal to simple y. Doesn't matter what the x value of x is. So therefore, it can be obtained by this thing f x y evaluated at infinity y. So this is the same as the probability that x capital X is less than or equal to infinity, but capital Y less than or equal to simple y, right? So x can be anything. So that is the meaning of that. Okay, so that's about the cumulative distribution function, joint cumulative distribution function. Now we will learn about the joint probability mass function, right? You know, we talk about probability mass function when you have discrete random variable. Here we are going to talk about the joint probability mass function of two discrete random variables. So again, similar to the notation of the univariate case, the probability mass function of joint probability mass function of x and y is denoted by p subscript x comma y, and this whole thing is the joint probability mass function of xy evaluated at xy point. Simple x is a real number and simple y is a real number, and the value of that function is obtained by as a probability. So that is the probability that capital X is equal to simple x and capital Y is equal to simple y. Right. So this is an event, this is an event. So this again, this is the probability of the intersection of these two events, right? It's defined as the joint probability mass function, right? So for all possible values of x, y, it is defined like this. So what are the properties of this function? Of course, it is a probability always, therefore it has to be between 0 and 1. But in particular, it has to be greater than or equal to 0, right? And then we know the total probability in a univariate case also, the total mass has to be equal to 1. So the same idea here, the total mass should be equal to 1. That means if you add pxy, simple x, simple y over all possible pairs of xy, then the answer should be equal to 1 for this pxy to be a joint probability mass function. So they are very obvious and direct extension of the univariate definitions. And then the marginal probability mass function of x and marginal probability mass function of y can be obtained like this. If you add the joint probability mass function over all possible of values of y, then you get the marginal probability mass function of x. Right. So here, if you are considering, for example, x equal to x naught, and here will be x equal to x naught. So in that case, you will be adding pxy x naught y for all values of y. Right. So like that, we can get pxx for any x value. And similarly, marginal probability mass function of y will be obtained by adding the joint probability over x. Right. So p by y is equal to the summation of pxy over all possible x's. And if you want to find out the probability that the random vector xy, right, this is called random vector or random point in this case, in the two-dimensional plane. Random point is in some set can be obtained by adding the joint probability mass function over all simple xy points in this set A. So A here will be some a discrete set of xy points, right? So adding over that, we will get the probability that xy equal to A. That means this is a particular event again. Xy is in this A, right? So that can happen in several ways. So you have to add this joint probability mass function over all possible ways like that. And then, of course, you can get the probability, joint probability, a cumulative probability function by adding the joint probability mass function for all uv values such that u less than or equal to this x here and v less than or equal to y, right? Because here this is the probability that capital X less than or equal to simple x and capital Y less than or equal to simple y. Right. So in this case, again, we are looking at a particular set A. That set A satisfies these two conditions, all the values less than or equal to simple x and all the y values simple less than or equal to simple y. So you have to add that over that set A. So this describes here, like here, the set A. Right. So here we are just using u and v because here I'm using simple x and simple y. If you use simple x and simple y here, that will be kind of confusing. So that's why we are using u and v. That doesn't matter as long as you are consistent with the notation. Right. So now I'm going to look at one example for this. For this, I have considered some real data. I have a large data set of the marks, large data set with marks for physics and chemistry of about 73,000 A-level students, right? So I have paired observations. Each person has a physics mark and a chemistry mark. And I have such pairs for about 73,000 students coming from A level, right? Uh, but the marks have usually numbers between 0 and 100. So I'm not going to look at the joint probability mass function of the marks of physics and chemistry. Then it will be like each probability mass function. I have to look at all possibilities of the combinations of those marks. So to reduce the dimension, I converted those marks into grade points, GP values, using this particular condensation, right? So if somebody has marks for some subject between 0 and 24 inclusive, I take that as the grade point as 0. And if the marks is between 25 to 39 inclusive, the grade point will be 1, like that. According to this table, I convert those marks into GP values. So for each person, there is a GP value for physics and a GP value for chemistry. And then I looked at all possible combinations. Now here there are 5 values. So 5 times 5, 25 possibilities, 0, 0, 0, 1, 0, 2, and so on. So I found out how many students have 0, 0, both 0 GP for physics and chemistry. How many students have 0 and 1? How many students have 1 and 0? Like that. By looking at that, so I divided those numbers by this number, the total number of students, to find out the proportions. So that gives me the proportion of students with 1 and 1, proportions of students with 1 and 2, like that. Then I got this table here. So that actually gives you the probability, joint probability mass function of this X and Y, where X is the GP value for physics, Y is the GP value for chemistry. Right. Actually, in a practical situation, we will not have that large sample. If you may have about 100 to 200, maybe, then still you can get proportions like what I explained, how I explained. But those will be not the actual probabilities. Those will be kind of estimated probabilities, estimated joint probabilities. But in this case, because I have a huge number of students, actually, I have the whole population. Therefore, these values have come from those population values. Therefore, these values can be actually considered as actual joint probabilities. Right. And this is the tabulate form that you can show a joint probability mass function of two random variables. And this is the graphical method that you can show, right, using this kind of uh, what you call line graph sometimes, right? So each possible, for example, this is 0 and 0, sorry, this is 0, 0, this is 1, 0, and so on. And the height of these lines show the uh, probability. Right. Now, there is an interesting thing in this table when you look at it. For example, if you look at those who got a zero GP value for X, that is for physics, there are people who got 0, 0, who got 0, 1, who got 0, 2, who got 0, 3, and who got 0, 4. Actually, those who got 0 for physics, there are no students who got 3 for chemistry and 4 for chemistry. Right? Only those who got 0 for physics have got either 0 or 1 or 2 GP for chemistry. Right, so that is one important thing. Those who got 0 for physics don't have high GP values, 3 or 4 for chemistry. And also, if you look at the highest proportion here, you can see those who got 0 for physics have the highest tendency to got 0 for chemistry as well. This is the largest proportion in this row. Right? So that is an interesting thing actually. Those who are weak in physics are more likely to be very weak in chemistry as well. And then if you consider this, those who got 1 for physics, right? They have not been able, nobody has been able to get 4 for chemistry. They have been able to very small probability, with small probability, very few students have got 3, but nobody has got 4 in that case. Those who have 1 GP value 1 for physics, that is one thing. The other thing is that out of these probabilities, this is the largest value. So that again tells you that those who get 1 for GP1 for physics have the highest tendency to get GP value 1 for chemistry as well. So this shows a very strong uh, relationship between the GP values of physics and chemistry. Right? And the same pattern actually exists for the other cases also. You can see that those who got GP value 2 for physics have been able to get very few people have got GP 4 for chemistry, little bit more than that GP 3, and little bit more than that GP 2, and so on. And that is one thing. Uh, And those who got two GP2 for physics actually don't get zero also for chemistry. Very, very few only get zero. Right? That is a good thing. And if you also look at highest probability here, you can see that those who get two for physics have the highest tendency to get two for chemistry as well. Right? This is the highest probability. So this is a really interesting thing that you can find out when you look at the joint probabilities. And the same pattern can be explained for GP for 3 and 4, right? So for example, if you consider 4, those who the best for physics, those who got 4 for physics, they never got zeros or ones. GP values for chemistry, right? Or even two, very, very, very little, right? All the other people got at least three or four for chemistry as well. And the highest percentage, therefore, uh, uh, highest percentage got for chemistry, right? So that's a very interesting thing actually. All the diagonal values are the highest value here, and the other important things that I mentioned, right? So so therefore you can see that there is a very strong correlation between these uh, GP values for physics and GP value for chemistry, right? If we studied these variables separately, we would not see this kind of patterns. So that's why studying multivariate relationships, studying multivariate variables is important, right? So this is the same table, but now I have added another column and I have added another row to show the marginal probability mass function. So if you add the rows, you get the right. So this is the marginal probability that x equal to zero, px0, that you obtain by adding these probabilities. And similarly, adding these probabilities, you get that this is the px1 value. Px1 is px2, px3, px4, right? So that whole thing collectively gives you the marginal probability mass function of capital X. And similarly, if you add the column values, you get the marginal probability mass function for capital Y, right? So this is P capital Y evaluated at 0. This is P capital Y evaluated at 1 and so on, right? Now you know that some of the marginal probabilities must be equal to 1. In this case, it is equal to 1, right? Some of the marginals, these also should be equal to 1, right? Because, and then of course, some of the joint probabilities should be equal to 1. So, excuse me. Right. So, but in practice, sometimes when you calculate these probabilities, because you are rounding them up and they are O down, or maybe rounding to a certain number of decimal places, then the sum will not be exactly one. There might be a slight difference. That's okay because that's occurring because of the rounding. Right. So that's about the joint probability mass function and marginal probability mass functions coming from the joint probability mass function. Right. Now we will look at joint probability density function. Of course, we cannot define joint probability mass function for continuous random variables. Right? You remember that this discussion we did when we were talking about univariate continuous random variables. I showed you that why a continuous random variable cannot have a mass function. Right? And there we define, instead of a mass function, we define the density function. And we define the density function as the derivative of the cumulative distribution function. The same idea comes here. We cannot have a joint probability mass function for two continuous random variables. Instead, we will have a joint probability density function denoted by f subscript xy. That is the notation, and then evaluated at some two a point real number x coming from real numbers x and y, and that is defined as the second partial derivative of uh, X is a mixed partial derivative of the joint cumulative distribution function, right? So you can first differentiate with respect to y and x, so it doesn't matter. Most of the cases, you get the same answer. It doesn't matter whether you differentiate with respect to x or y first, right? So, what are the properties of that kind of joint probability density functions? Of course, the joint probability density functions have to be greater than or equal to zero, greater than or equal to zero. But these are not probabilities. That is an important thing to understand. These are not probabilities. They are joint probability densities. So in that case, the densities can be even greater than one, right? Like not like probabilities. Probabilities have to be less than one or equal always, but densities for a single random variable or even a joint probability density can be greater than one. But of course, it has to be greater than or equal to zero always. It cannot be negative. And the total integral of the joint probability density function over the whole uh, uh, area, x from minus infinity to plus infinity and y from minus infinity to plus infinity, should be equal to 1. So again, similar to the univariate case. And then marginal densities, that is just the density function of x and density function of y, can be obtained from the joint density, similar to what we did uh, in order to get the marginal mass functions. We added the joint probabilities over y, right, in order to get the mass function of x. Here we have to marginal density function. In order to get the marginal density function of x, we have to integrate the joint density function with respect to y. So it's like adding over y for all possible y values. That is integrating from minus infinity to plus infinity. So dy means adding, it's like adding over y. And similarly, in order to get the marginal density function of y, you have to integrate the joint probability density function with respect to x over the whole possible range of x. So they are very similar to the univariate cases. Uh, the discrete mass function case, joint probability mass function, except as a summation, you have the integration here. And then if you want to find out the probability that the random vector or random point, capital X, capital Y, is in a certain particular region in the two-dimensional plane, R, say, then you have to integrate the joint density function over that region R with respect to X and with respect to Y. So that is the general definition here. But in a practical situation, the limits of these integrations we have to define accordingly, so that to define this set R, right? It doesn't have to be always from minus infinity to plus infinity. Uh, so it has to be over that particular region R only. Right? And of course, we are usually obtaining the joint probability density function, right, according to the definition, by differentiating the joint probability, cumulative probability function. So therefore, if you integrate the joint probability density function, you should be able to get joint cumulative distribution function, capital F. So that's right. Now we will look at one example uh, to answer some questions like finding the marginal densities and calculate some probability uh, using a given probability, joint probability density function. Right. This is not coming from Demidenko's book. I have obtained this from some other book. Actually, this is also in the internet. It's a kind of interesting question. A nut company markets cans of deluxe mixed nuts containing hazelnuts, almonds, cashews and peanuts. Let capital X denotes the proportion of cashews in a randomly selected can, and let Y denote the proportion of almonds, of course, in the same can. Suppose the joint probability density function of capital X, capital Y is given by this particular formula here. Then the question is derive the marginal probability density functions of X and Y, and then compute the probability that two types of nuts, that is cashews and almonds, make up at most 50% of the can. Right. So according to this thing, X denotes the proportion of cashews, Y denotes the proportion of almonds, uh, but the can contain the other nuts also. Uh, Therefore, that's why we say here X also, of course, has to be greater than or equal to 0. Y, so this X is the amount of observed, for example, real number that you are calculating the joint density, right? So this X has to be greater than or equal to 0, Y has to be greater than or equal to 0, and X plus Y, which will give you the total proportion of cashews and almonds, has to be less than or equal to 1, uh, because there can be, in addition to these two, there can be some other, maybe only one remaining nut. So maybe there are altogether four types of nuts: hazelnuts and almonds and cashews and peanuts. So in addition to cashews and almonds, there might be peanuts and hazelnuts as well, right? So therefore, X plus Y can be less than 1. In that case, the other two will fill the other part, remaining part. If X plus Y is equal to 1, in that case, the other two will not, on the other two types of nuts will not be there. Right. So, but they have obtained this particular expression 24 times xy for this joint probability density function. Right. So in usual problems, you are given functions like that, but as practical statisticians, we should think how this joint probability density function was obtained by them, right? Or in general, how one would obtain the suitable joint probability density function for two random variables, right? That's an interesting question to ask. So therefore, I also looked at that question. And so in addition to the answers to these two questions, I will also briefly discuss about that. Generally, there are several methods that one can apply. That is, there can be some theoretical purposes, formulas that should follow, that probability density function should follow. There are rare cases like that. But more practically, usually these are coming from data, right? If somebody has a large number of a set of observations uh, containing what percentage of each nuts were there in different cans, right? So using those, we can find out, for example, if you are interested in XY only, then you can look at uh, in one can, what was the proportion of X, what was the proportion of Y. In another can, what was the proportion of X, that is, what is the value of X, what is the proportion of cashew, and what is the proportion of almond. That is, what is the proportion of X and what is the value X and what is the value Y. In another can also, you can observe X and Y. And from another can also, you can observe X and Y. Like that, you may, if you have large number of XY values, each can has a X value and a Y value, right? Paired observations. Then from that, we will be able to find out what are the available combinations of these X and Y, and then thereby look at what percentage of observations are in those particular combinations. And using those, then we will be able to write. So, for example, X equal to 40% and Y equal to 30%. There are, say, 50 observations in my data set, right? So, therefore, I can find out the proportion, right? 50 divided by the total number of observation for that particular category. So like that, I will have large number of possible categories. For those, we'll have data, and then maybe plotting X, those uh, percentages versus X and Y, right? Taking and plotting it as a three-dimensional graph, right? X is in one axis, Y is the other axis, and then the frequency will be the height. Then we will be able to get roughly some idea about the shape of the surface connecting those heights, points, right? That is one way, right? Or you can maybe use some kind of a regression analysis where those percentages are the response variable, and then X and Y will be explanatory variables, and then try to fit a model for those proportions. And then that will give you an idea about what the density function should look like. That is another method. Uh, Another third method is using a well-known model and fit that model and see whether that model fits the data well, right? So first you fit it using the data, and then after fitting the model, you can see whether the data actually fits it well, right? So if you consider that method here, uh, we are considering the joint distribution of proportions, sample proportions, right? Proportion of cashews and proportion of almonds, sample proportions, right? So therefore, it's better to look at some models available for joint probability density functions for proportions. Proportions are continuous random variable. So X here is a continuous random variable, Y is a continuous random variable, right? So if you look at that kind of models available, one important model is called Dirichlet distribution. Dirichlet distribution, right? So one might try to fit a Dirichlet distribution for this X and Y. Yeah, both X and Y are proportions, sample proportions. And then later on check whether that fit is a good fit. Right. So therefore, let me briefly explain what the Dirichlet distribution is, and then you can understand how it could be used to find out the a suitable model in this case uh, for the joint probability density function. Right. So the Dirichlet distribution is actually the multivariate generalization of the beta distribution. Right. You may recall that we discussed about this beta distribution in one of the lectures. I have given you that video. Uh, so that is used as the model for the density function of some random variable, continuous random variable, when the support of that random variable is a finite interval, right? Length of the interval is finite. That means between some A and B, where A and B are finite numbers, right? Especially the standard beta distribution is used to model the density function of continuous random variable when the random variable is between 0 and 1. Possible values as support is 0, 1 interval. So this Dirichlet distribution is used when you want to model the joint probability mass function of several random variables where each variable is a proportion, like for example, between 0 and 1. Right? So we have a situation like that. So in general, if there are k such variables, where the sum of those k variables proportions is equal to 1, then people use Dirichlet distribution uh, as the as a possible joint probability density function for those x1 up to xk. In our notation, these are x1 up to xk, or otherwise they may be proportions, several k proportions, right? So in that case, the density function of the Dirichlet distribution is given by this formula here, right? Then the random vector is said to have random vector x1 up to xk. Is said to have Dirichlet distribution with parameters. It has k parameters uh, given by this density function, right? So This is the normalizing constant, and then x1 alpha 1 minus 1, x2 to the power alpha 2 minus 1, and so on, xk to the power alpha k minus 1. So that is the general form of a Dirichlet distribution. In our case, this is the notation that is used, like in the binomial case, Poisson case, we have some notation. So similarly, this random vector has a Dirichlet distribution with these parameters. That is one commonly used notation, right? So to connect our problem to the Dirichlet distribution, notice that we have three variables like x1, x2, x3. Here we have x, y, z, where x is the proportion of cashews, y is the proportion of almonds, and let's take z to be the proportion of other nuts. So that will be therefore 1 minus x minus y, right? So even though there are three variables, actually, there are only two variables which are free to move because z has to be always 1 minus x minus y, right? So he have a situation where x plus y plus z is equal to 1, and all the x and y and z's are between 0 and 1. They all are greater than 0. Therefore, theoretically, we can we can probably try the joint distribution of x, y, z to be Dirichlet, right? So if that is the case, then if these three variables have a Dirichlet distribution, we need to talk about three parameters: alpha 1, alpha 2, alpha 3, right? So you can write down the density function, evaluate density, joint density. So here I should have written f of subscript x, capital X, capital Y, capital Z, separated by commas, but I have not written it like that. So f at x, y, and then there should be a z also generally. Then it will be x here, y, z, and this part will be z in that case. This part will be z. But I am interested in only x and y, and z is actually not free to vary once x and y are given. So therefore, I have written down z also in terms of x and y. Therefore, I have this density written in terms of x and y only. Right. So this is the suitable model in that case. Right. So f uh, subscript capital X, capital Y evaluated at simple x, y given by this expression is probably suitable model, right? So in order to see whether this model is suitable or not, first we have to fit the model. That means we have to estimate these parameters using the data. So if you have data, enough data, we will be able to find out suitable values for alpha 1, alpha 2, and alpha 3. There are several methods for that. One method is called the maximum likelihood method, for example. So using that or some other method like method of moments is a simple method, right? Using that kind of methods, we can find out some suitable values for alpha 2 and alpha 3. Okay. So probably these people have done something like that. We don't know whether, because those books don't tell how they got the density function. But we can see that actually, theoretically, the density function that they have used and the density function coming from, if you assume Dirichlet distribution, will match like this. For example, you can see this is of the form of this form, right? You have a constant and then x to some power, y to some power, and then z to some power is not appearing here. But if alpha 3 is equal to 1, that part will disappear, right? So therefore, what we are considering may be a special case of the Dirichlet distribution, right? Without the z part, right? So this may be considered as coming from this distribution with alpha 1 is equal to 2. So that's 2 minus 1 here and 2 minus 1 here, 1 minus 1 here as the powers, right? And then, of course, if that is the case, then the normalizing constant should be this constant. And actually, if we calculate this constant using those alpha 1, alpha 2, alpha 3 values that we mentioned here, we actually get 24. So it might be that they have estimated using the data, assuming the Dirichlet distribution, they might have obtained alpha 1 to be 2, alpha 2 to be 2, and alpha 3 to be 1. And thereby, the normalizing constant must be 24, and therefore they decided to use this model. Maybe that is the way that they did it. But anyway, I brought this discussion for you to uh, think about this always without just taking the formula somebody else has given. We also have to think what will happen if we were going to do this. And from the beginning, we will need a model for that, first of all. Then only we can answer uh, other questions, right? So therefore, we have to think about how to get a suitable model also. Right. So that was an addition part actually to the. I mean, we don't need that part to answer these two questions, but I think it was an interesting and important thing. Right. So now we will come back to answer these questions, part one and part two. So we will first derive the marginal probability density function of x, right? Marginal density function of x. So given the joint density function, we have already discussed how to get the marginal uh, density function of x. Right. So I have here drawn, just to get an idea about what this joint probability density function looks like, right? So it is defined on a triangle, this triangle here from here to here, and then connecting this corner to the other corner, right? Because x plus y has to be less than or equal to 1. X can be between 0 and 1, y can be between 0 and 1, but x plus y has to be less than or equal to 1. So this surface here given by 24 times xy is defined only on this triangle on the left, right? On the triangle on the right, of course, the density function is 0, right? So this is what the joint density function look like. Now, from this, we want to get the marginal distribution function of x, right? So, if I want to get the marginal distribution function of x, let me consider a fixed point, right? This is the x-axis. So, let me suppose I want to get the marginal density function of x uh, at say this point, right? So, what is fx point 3? Right. So what I have to do is, as I explained earlier, we'll have to integrate the joint density function fxy at point 3 y with respect to y, right? So you have to consider if you want px here, then joint density function at xy. But what I want is fx at point 3. So in that case, I have to consider fxy point 3y dy. So what is this fxy 0.3y? So that is actually whatever the curve or straight line or whatever you will get if you cut this surface vertically at x equal to 0.3, right? If you cut this surface vertically at x equal to 0.3, you will get some function here. You will see if you look at from this side, the y-axis side, you will see a certain curve, right? So that is the curve given by this fxy 0.3y. So that will be a certain curve, and thereby there will be certain area, right? Right. Like this. This is the line on the floor here, right? So you will see this kind of area, right? And then you have to get the that area by integrating this function. So that will give you the area under this curve. But you have to integrate with respect to y. So what are the limits that you have to use? You have to use the y is changing from 0 to some point here. Remember, we are looking at x equal to 0.3, right? But we know that x plus y is less than or equal to 1. right? So y will be therefore less than or equal to 1 minus x. So in this case, y will be less than or equal to zero point 0.7 because x is equal to zero point 0.3. So therefore, in this case, you will have to integrate from 0 to zero point 0.7. Y will be changing from 0 to zero point 0.7. So that will give you this answer, right? And similarly, if, so that will be this height here. Not this one actually. Well, this one. When x equal to this thing, the density function has this one. So if you evaluate this thing, the answer should be something like this. And similarly, if you want to calculate the marginal distribution function at say zero point 0.6, then you will have to first think of cutting this surface vertically at x equal to 6. Then you will have a certain uh, uh, face. You will see a certain face uh, from this side. If you look at from this side, you will see a certain area. What you are finding is that area. In order to find out that area, you have to integrate whatever it is. If it is a curve or a straight line, whatever, you have to integrate that with respect to y from this value to this value here, right? So that will be again 1 minus zero point 0.6. So generally, therefore, if you want to get fx at x, then you will have to integrate fxy evaluated at xy dy. Y will be changing from 1 to 0 to 1 minus x. 0 to 1 minus x, right? So that's how you will have to get a general expression. Otherwise, you can get fx at different values, right? And in that case, that different value have to be here, put here, and then get that value, right? So, and similarly, if you want to get the marginal density function of y, you have to consider, let me first delete this one. You will have to consider, for example, if you want to consider the marginal density function when y is equal to zero point 0.4, in that case, you will have to think of, like, imagine you are cutting this surface along this line, and then when you look at from this side, you will see a certain uh, curve, right? And then you can find out the area under that curve. In that case, you will have to integrate with respect to x, right? Integrate with respect to x. X will be changing. So this is the x equal to 0. X will be changing from this to whatever this point here. And then in that case also, x will be less than or equal to 1 minus y. If y is equal to zero point 0.4, x will be changing from 1 to zero point 0.6, right? So in that case, similarly, you have to do the integration, right? So I have prepared a Shiny app to show this little bit better than, because my drawing is not good here. I have prepared a Shiny app. So now let me take that Shiny app um, to show you this or explain this little bit better, right? Um, so I want to, for the moment, I want to, yeah, okay, right. So this is that Shiny app, right? So let me show you the thing that I was explaining earlier using this Shiny app. So let's, for example, suppose I want to find out the marginal density function of capital X evaluated at, say, zero point 0.3. So this is zero point 0.3. This is x-axis. This axis can be considered as y, but actually y-axis on this here. So 0 to 1 here, and then 0 to 1. But because if you consider that to be y-axis, you cannot see the scale. Therefore, scale is on this side. So now, as I mentioned, if you want to find out the marginal density of x evaluated at zero point 0.3, you'll have to consider uh, cutting this surface vertically along x equal to 0.3 line. And then you will see a certain curve or a straight line, whatever, on the surface if you look at from this side, right? So in this case, actually, if you cut at point 3, this is the line that you would be going through on the flow here, right? So it's going to a certain point here on the flow, and this will be the cross section that you will see, and this is actually that cross section that you will see when you cut this thing when vertically at x equal to point 0.3. So what we will be getting as the marginal density function of x evaluated at point 0.3 is actually the area in this cross section here, right? Under the under this curve, right? So this is the curve actually f joint probability density evaluated at x equal to point 0.3, right? So it's a function of y only. Right. So in order to get this one, you have to integrate that function from y equal to this from this point to this point. But as I mentioned earlier, this is y equal to 0. At this point, y will be equal to 1 minus x because x plus y must be less than or equal to 1. Right? So therefore, you will be integrating this straight line here from 0 to 1 minus x, where x is equal to point 0.3 now, and you will get this value. This is the height that you get. So when x equal to point 0.3, therefore your marginal density will have this value. Right? So let me show you what will happen if I consider, say, for example, x equal to point 0.4. Right. So in that case, I'll be cutting vertically this axis at this point, right? And this is the cross section that I will see if I look at from this side after cutting. And so what I need is the this area of this triangle in this case. So you can get, in this case, it's a triangle. I will show you why it's a triangle, because this becomes a straight line. So it's going to be a triangle. So in this case, actually, you can easily find out the area using geometry, or you can integrate this curve from 0 to 1 minus y, and then you will get the answer. So in this case, this is the value that you get, right? So like that. So let me change this value where I'm considering this uh, x value. And you will see that this area is changing, and therefore this height is changing, right? So I'm moving this line to this direction. So you can see that you will see that it's getting smaller and smaller, this one, right? Area will be smaller because this, right, even though this thing becomes larger, this width of this, right, range becoming smaller and smaller, right? And therefore, finally, the area is becoming smaller, right? So like this. So if I go back to the other side, you will see that's increasing to a certain extent, the height of the marginal density, and then it is going to the other direction. So therefore, it's decreasing again, right, like this. So let me show path of that dot here. When I was changing the x value from here to here, this is the path that you will get. So when the considered x value is changing from 0 to 1, right? So you'll see now, for example, if I increase, right, you can see that this point here, this point here is going along this curve, going on that curve actually. So that is actually, that curve actually is the marginal density function of x in this case, the marginal density function of x. Right. So similarly, you can look at the marginal density function of y, but I have not included that in this Shiny app. But anyway, I hope now it's very clear to you what we mean by the marginal density function obtained from a joint density function. Right. So now I come back to my slides. Right. So if I discuss the same thing further again, so this is the joint density function that we are considering. So let us consider a particular x naught value like zero point 0.3. Then the cross section becomes 24 times x naught times y. Right? X naught is fixed. Right. So therefore, this whole thing is fixed times y. Right. So you can see that it's a straight line in terms of y. So that's why you saw that the cross section was a triangle. Cross section was a triangle because this is a function of y, and this is actually not only a function of y, this is a linear function of y. The z represents this part, right? That's the height, right? So you can see that's why the cross section was a triangle in this situation. So what you needed was actually the area of that triangle. So we can obtain by looking at now at the highest point, uh, y will be equal to 1 minus x naught, right? So that will be the height of the triangle, and the width of the triangle, that will be the length of the range when range of y when x is equal to x naught, that is equal to 1 minus x naught. So from that you can easily get the area of the triangle. That is one way in this particular case, but in general we will not do that. What we will do is we will integrate the like this to get the density function. So fx at x naught will be integration of this one, 24 x naught y dy. Y is changing from 0 to x naught, right? So this is what you get. So generally, for general x, you will be considering fx x 24xy with integrating with respect to y. But in that case, the limits will be from 0 to 1 minus x. So finally, this will be 12 times x times 1 minus x square. Right. So that you can see that's a quadratic, not only quadratic, actually a cubic function. Right. So that was the function that I showed you here. So this is that function in that range. It looks like this curve here. Uh, so, so in order to get the general expression, right, cumulative, sorry, the marginal density function at x, this is what you do. You integrate the joint density with respect to y, and this is the limit. Right. You can get that idea from this also. So when you are finding this kind of marginal distributions, it's not easy to draw the whole surface. But what is more important is actually the support of the density function. So this large triangle is the support of this particular density function, right? X from 0 to 1, y from 0 to 1, and x plus y less than or equal to 1. Right? So if you want to get the marginal density function of capital X at some value, say simple x, what you have to do is you have to integrate the joint density. Let's consider some point here, say x here, x. Right. So at this point, you want to find out fx, x. So you have to integrate the joint density function along this axis, along this line from here to here. So fx x is equal to the integration of the joint density xy with respect to y, but the y will be going from 0 to 1 minus x, right? Because if the value of x is here x, and then the y value will be 1 minus x, right? Because this line is x plus y is equal to 1, right? So y value is equal to then 1 minus x. So therefore you will be integrating from 0 to 1 minus x. And similarly, if you want to get the marginal density function of y at some value, say simple y, right? Say this is simple y. So in that case, f y y is equal to the integration of the joint density f x y evaluated at simple x y dx, right? But now x is changing from 0 to this point. Here x is equal to 0. This point is equal to 1 minus y. X is equal to 1 minus y, right? We are fixing this y value now. So at that point, x will be 1 minus y. Therefore, this will be from 0 to 1 minus y, right? So you are integrating with respect to x and then putting the limits in terms of y. So finally, it will be in terms of y, right? Right. So we have got, using that, we have got this expression 12x times 1 minus x square, where x has to be any value between 0 and 1. And similarly, if you do the calculation, you will see that fyy will also be in the same form. It will be 12y times 1 minus y square, because you can see this density function is uh, symmetric of x and y. You can exchange x and y without any change of the function. So therefore, fyy will be integration of this thing with respect to x from 0 to 1 minus y. The expression will be finally 12y times 1 minus y square, where y will be between 0 and 1. So you don't have to do it separately by symmetry. You can get that directly, right? Okay. And then we will look at the last part, how to find out the probability, right? We want to find out the probability that x plus y less than or equal to zero point 0.5, right? So this condition actually specifies a certain event, and in terms of geometry, it gives you a certain sub-region of the support, right? What is that sub-region of the support specified by this thing? That is simple x plus simple y less than or equal to zero point 0.5, right? So that is actually this blue area, right? So I want to find out what is the probability that capital XY random point will be in this area. For that, I have to integrate the joint density function over this area, right? I have to integrate the joint density function over the whole area, right? So if I call this, for example, A, if I say this is A, the probability that x, y belongs to A is given by integration of the density function, joint density function with respect to x and y both over the whole points, all points, xy points in this area, right? But if you write down like that, that's not going to give us a value. Therefore, what you have to, actually, this will be double integration because we are integrating with respect to 2. So this has to be, right? Fxy, of course, we know the expression, we can put it there. What is important here is uh, the limits here, right? Actually, you can write down, if you are going to integrate with respect to y, then put the limits of y here. And then if you write down x first, you have to write down the limits of x. But I usually, it is convenient for me to look at fix x and then change y values and then finally change x. because I like to consider the vertical stripes here. So let me consider a vertical stripe here at some value x here. Sorry, this line has to be, so I'm considering a small stripe with a small width, right, at some value x, and suppose this is dx. Right? So what I will do first is find out the volume under this small vertical stripe spanned by the density function. So in order to find out that, I have to integrate the joint density function with respect to y, because y is changing here, x is fixed. From this point to this point, right? So I will consider that first, integration with respect to y, from where to where? This is 0, y equal to 0. This value is y equal to 1 minus x. Sorry, not 1 minus x, zero 0.5 minus x, because this line is x plus y is equal to zero 0.5. So therefore, this point here, y value will be zero 0.5 minus x. So you have to integrate this thing with respect to y from 0 to zero 0.5 minus x. So then everything will be in terms of x now. Sorry, yeah. You are with so this is y, and then we have to integrate with respect to x. So this will be now everything will be in x. So you can now integrate with respect to x and put the limit for x. So in order to cover this whole blue area, x has to change from here to here, right? So therefore x will be from 0 to zero 0.5. X has to change from there to there. Right? So that's how you will find out this probability. So that's it. I'm integrating with respect to y first. This is the joint density mass function, integrating from 0 to zero 0.5 minus x first, and then integrating with respect to x from 0 to zero 0.5. Right? So when you are integrating with respect to y, this 24 times x will be considered as a fixed value, and then y square divided by 2 will come, and then once you put the limit in terms of x, everything here will be in terms of x like this. And then you integrate that with respect to x and then put the limits. Then you get this answer here. And finally, answer is 1 over 16. Right? 1 over 16. That is the probability that x plus y uh, uh, will be less than or equal to zero 0.5. That is the same as uh, xy point is in this particular set A. Right. So that I think explained in great detail uh, how to find out the marginal density functions and a probability regarding using the joint probability density function. Right. So we will look at another example now. Uh, a bank operates both a drive up and walk up window on a randomly selected day. Let capital X denote the proportion of time that the drive up window is in use. That means at least one customer being served or waiting to be served. And let Y denote the proportion of time that the walk up window is in use. So both X and Y are certain proportions, right? So let us, we are given somehow the joint probability density function of x and y as this function. Now notice here, we don't have any restriction in terms of x and y here. X can be any value from 0 to 1, y can be any value from 0 to 1 because they are proportions, but there is no restriction like in the previous situation, like x plus y less than or equal to 1 or something, right? So therefore, according to this thing, the support for this density function will be the square, right? It will be a square from 0 to 1 on the x side, and then from 0 to 1 from y side. So it will be a square with 0 to 1 in both sides. So what is the question? Find the marginal probability density function of x, marginal probability density function of y, and find the probability that neither facility is busy more than 1/4 of the time. Right. So we look at those things. But first of all, to clarify what these random variables are, because they say that it's the proportion of time particular window or particular window, walk up window or drive window in use, right? So in order to define that, if the bank is open for T minutes during the day and drive-up window is in use for D minutes, in that case, X will be D divided by T. So both are in minutes. So X will be the proportion of times in minutes uh, divided by the proportion of the total time that the bank was open, right? And similarly, Y will be W divided by T, where W is uh, the time that the woke-up window was in use, right? So we are looking at the joint distribution of this X and Y, and it is given to us. Again, we don't know how they obtain it. They might have used the data or maybe some other method. So if I draw the joint density function, this is the surface that I get. So as I mentioned, it's over the whole square here, 0 to 1, and then from 0 to 1 here. It's over the whole square, right? But here, if you look at this function, it's kind of linear in terms of x, but quadratic in terms of y. So it's not a flat, it's not a flat surface. You can see it's a small curve going up here. So that's because of that y square term, right? And what I have shown here by these red lines and curves are the marginal densities. So this is the marginal density function that we would get for x, marginal density function of x, and this is the marginal density function of y. And this is actually a straight line. In this case, it's not a straight line, it's a curve, right? And I have drawn these things actually after I have obtained these things. So let's see how we obtain, right? So again, it's easy, and I recommend always for this kind of problems for you to look at the support first. I draw the picture of a support. Then you can see if you want to do some integration, what are the limits going to be, right? In this case, actually, limits are not difficult to think because x and y are free to vary from 0 to 1, right? The range of x doesn't depend on the range of y, right? Value of y, right? But anyway, this is the support, this large, say, actually, it's a square from 0 to 1, one side length 1, the other side length 1. So that is the support. So if you are finding the marginal distribution of capital X at some value, in that case, what you have to do is, say, for example, we are finding the marginal distribution of X at 0.6. So I'll have to integrate the joint density over whole of this line, right? From 0 to, I have to integrate in order to get Fx. So I'll write down it for general X, right? So I'll have to integrate this particular joint density function xy with respect to y, but the y will be going from 0 to 1 in this case. It's very easy in this case. And right. So similarly, fyy will be equal to integration of xy evaluated at xy dx. And in this case, you will be considering a particular x right here. Sorry, a particular y. We want to get the marginal density at that value, but we are integrating with respect to x. X goes from 0 to 1 again. So 0 to 1. Right? So those are the two expressions that we have to simplify to get these two. But of course, in this case, fxy is not symmetric in x and y. So therefore, the two expressions will be different. So let's see what we get. So fx is going to be the integration of the joint density from 0 to 1 with respect to y. So you are different integrating this with respect to y. So in that case, this term will be considered as fixed, but this term will be integrated. So therefore, you have the 605 can be out, but then x times y and then y cube divided by 3. So you have to put the limit from 0 to 1 to get the marginal density. So this is the density. You can see that's a function of x, and it's a linear function of x also, right? So that's why you saw that here. This is a straight line here, linear function with a positive slope, right? Uh, and yeah, the slope is 605 and the intercept is equal to 205, right? So that's a straight line. In order to get the marginal density function of y, of course, again, you have to integrate the joint density function with respect to x from 0 to 1. But now, because you are integrating with respect to x, this will be considered as y square will be a fixed value. X is a, you have to integrate x, so it's x square over 2 will come, and then x y square like this, and then put the limits for x, right? You put the limits for x, not for y, right? So this will be 1 will be put here, 1 will be put here, and then 0 will be here. And then finally the answer will be in y. And y has to be between 0 and 1. So that is actually, you can see that's a quadratic function. So that's why you saw here, this is not a straight line, that's a quadratic type function. This is the marginal density of y, that function. Right? And then the final part, we wanted to find out what is the probability? Find the probability that the neither facility is busy more than one part of the time. So that means what is the probability that x is less than or equal to 0.25, that is 1 over 4, and y is also less than or equal to 0.25, right? What is the probability of that joint event, right? So we want to look at this probability x less than or equal to 1 over 4 and y less than or equal to 1 over 4. So this happens when x comma y is in a certain rectangle. That rectangle is this rectangle in a certain area A, right? So this is 0.25, this is 0.25. So what we are looking at is what is the probability that the random point capital X, capital Y is in this rectangle. In this case, is a square again, right? So we have to, what we have to do is now we have to integrate the joint density uh, over the whole area here. So again, if I want to integrate over the whole area, uh, there are, you can integrate with respect to y first and then x, or x integrate with respect to x first and then y with respect to y later. But I usually like to consider the vertical line when you are considering the integration here. So in that case, I will be first considering a certain vertical stripe, right, with dx width. And then along this line, I have to differentiate with respect to y. X is first fixed and then first differentiate with respect to y, but the limit of y will be from 0 to 0.25. Right, so that will be the first integration from 0 to 0.25 f x y d y. And then you have to integrate that thing with respect to x. And then in that case, x will be going from here to here. Then all the area will be covered, and therefore the volume below the surface will be calculated. So this will be from 0 to 0.25. Right. So that is the probability that capital XY point is in capital A. In other words, that is the probability that x less than or equal to 0.25 and y less than or equal to 0.25. Right. So we have got that. It's going to be this value. Right. Okay, so those are two good examples, I think, for you to learn how to find out marginals and how to find out probabilities. And then I have included an important bivariate distribution, bivariate normal distribution, just to show you what the shape of that is. Bivariate normal and trivariate normal, and even more than three variables, then we just call it multivariate normal. Those are very useful models when you are dealing with multiple variables simultaneously, right? So bivariate normal distribution contains five parameters: mean of the x, and standard deviation of x, mean of y, standard deviation of y, and in addition to that, the correlation between x and y. Those are the five parameters, right? And here I have considered the bivariate normal distribution with a given mean of x. I have considered mean of x to be 50 and mean of y to be 75, standard deviation of x to be 5 and standard deviation of y to be 10. But I have left the value of rho as a parameter because I want to see what are the differences in the how the joint density function changes when rho is changed, keeping other parameters fixed, right? So this is the joint density function of a bivariate normal distribution with those values: mean of x 50, mean of y 75, standard deviation of x is equal to 5, standard deviation of y is equal to 10, and rho is to be given. The value of the rho is to be given, right? So these are two special cases. This is what you get when rho is equal to 0. This is when rho is equal to zero point 0.7, where rho is actually the correlation coefficient between x and y. So you can see that when rho is equal to 0, these contours are the lines where there is equal height of the density function, right? So you can see that the uh, contours are circles here, but on the other hand, contours are ellipses here, right? So that is the main difference between the joint densities of a bivariate normal distribution depending on the value of rho, right? When the value of rho is equal to 0, actually, that joint density function, bivariate normal density function, is equal to the product of two individual normal densities. Rho is equal to 0, right? But here it's not like that. Rho is included and therefore it's not a product of two things. It's a different density function and it has this shape and these other contours. So that's all I wanted to show at this point. We will be looking at these models later on in a lot of situations, right? But because these are very useful and well-known distribution, I thought I should show the differences and general form of the density function, right? Okay, I think I will stop this part of this video here, and the next part will be discussed in part two, right? Okay.